Hey there, chemistry team. Chemistry coach coming at you with video number 4 of our thermodynamics series. A little bit of review for this one. We're going to look at the cornerstones of thermodynamics, the laws of thermodynamics. It's kind of like you got a stool. You can't have one leg of a stool, you fall over. You can't have two legs of a stool, you'd fall over. Three legs though, you're doing good. Four legs, you're doing good. Horrible analogy, but you get the idea. So I'm going to go through the main three laws of thermodynamics, first, second, and third. There's actually a zeroth, but we don't really utilize it distinctly in this class, so I'm not going to go through the zeroth law of thermo. If you want to Google that one, go for it. So we'll do the first, second, and third. Now, the first law of thermodynamics, almost all the equations we're going to be using are somehow derived from these. So we've got to go through and know these particular things. First law we covered last semester in first semester general chemistry, and that was the law of conservation of energy. I've seen many different ways to define this. Energy of the universe is constant, yada, 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 that kind of stuff. Energy cannot be created or destroyed, only transformed. However it's defined, the main thing is that there's energy constantly transforming from one form to another. For example, I turn the lights on in this house. Where does that light energy come from? Well, it comes from the filament, right? And that gets really hot. Have you ever touched a light bulb or something like that? It gets hot. Well, where does that energy come from? So you've got the heat energy, you got the light energy. Well, it's coming from electricity. Where does that come from? Well, it's coming down from a wire. And where's that ultimately coming from? It's ultimately coming from some kind of fossil fuel or a hydrothermal source or a solar. We got solar panels on our house. And so I can take, solar energy, convert that to electricity, convert that to light energy, to heat energy, coal. You can burn the coal, create heat, use that to heat up water to form steam. That kinetic energy can turn a turbine, in a magnetic field, creates electricity. I mean, on and on and on you could go, right? It can only be created or destroyed. This gives us, if you look back last semester, a couple of equations we used. We used this one, where the change in the internal energy of a system was equal to the heat plus the work, right? The only way to change the internal energy of a system was to either have it do work on the surroundings or vice versa, or transfer energy via heat to the surroundings or vice versa. Go back and review your thermochemistry stuff if you don't remember that. Also, we had another equation we got from that. If there's no work being done, then the heat of the system was always equal to the heat of the surroundings numerically, but different in sign. And it really doesn't matter which side you put the negative sign on. But if heat flows from the system to the surroundings, well, the surroundings must be accepting exactly the same numerical value of heat that the system lost, because the system and the surroundings, add those together, that's the whole universe. That heat has to go somewhere, right? So the system loses it, it goes to the surroundings, or vice versa if it comes from the surroundings to the system, right? So whichever one is losing it, we put a negative sign in front of, but you end up with the same mathematical thing. So in this case, if heat's going from the surroundings to the system, the energy of the system is increasing, same numerical value, just put a negative sign there. So we'll utilize these to derive some really interesting formulas and equations later on down the road. There's kind of a layman's term for this, says you can never win the game, right? You can never get more energy out than you put in. So you can never win. Let's go to the next law, right? It says you can't even ever break even, right? So you're always going to lose. That's the second law. So let me put up the second law of thermodynamics. This is review. Go back and if you want some more details, review this one in some of the prior videos or worksheets and PowerPoint reviews and whatnot from last semester on thermochemistry. So let me put up the second one. This one's a little different, but goes with what we have been talking about. All right, team. Hopefully the second one makes sense with the first few videos on entropy, because remember, enthalpy, heat, that was last semester, right? And I'll throw little snippets in here, but again, review it. Entropy is what we're really introducing here, and then we're going to combine these two later for Gibbs energy. All right, second law. This is specifically for a spontaneous process, not any process, a spontaneous process. The general overriding rule if something is spontaneous, occurs on its own as written without any outside help, the net rule for that, the law for that, is that the total entropy of the universe must increase. The overall trend is towards disorder, and you see that in your everyday life, right? That you might be focused on just the system, right? I could be focused just on my kid's bedroom, right? Or just on that car that's been sitting across the street. It's got the spider webs, under the tires and been sitting there for a long time looking under. I might be focused on just that system, but you really have to look at the system and everything around it. So the total entropy of the universe must be greater than zero. Must be the change in the delta S, the change in entropy must be positive for the whole universe. Well, the universe is the system plus the surroundings, right? So if you take the entropy change of the system, that localized part of the universe you're focused on, and add the change in energy of change in entropy of the surroundings, that should be greater than zero. So you might have a localized ordering effect where the change in entropy is negative, right? I cleaned up my bedroom, right? Got the rust off of that bumper, or things like that, or organized a deck of cards that was all over the ground, right? So that's a negative entropy change. But if you look at a spontaneous process, if it happens on its own, the change in entropy of the surroundings must overcome the change in entropy of the system. You could have a negative delta S system, but the positive delta S of the surroundings must be greater than that. So the overall amount is greater than zero. And we're going to use this later to derive some interesting equations. It's going to be quite the journey, but follow through. This is going to be important. And the layman's terms for this one, and again, the first law of thermodynamics was you can never win the game, right? But the second law says you can't even break even. You're always going to lose because the universe is always driving towards disorder. Bummers. Let's look at the third law. All right, third law seems less relevant to most people than the second law, but this will have some ramifications for calculating entropy changes later. And I'll talk about that when I'm done here. So third law of thermodynamics says that a perfect crystal, right? No impurities, just it's perfect, theoretically perfect. My wife is perfect. Okay, anyway, perfect crystal at 0 Kelvin. So we are at absolute 0 Kelvin. Can't get any colder. Total, complete lack of motion. Remember, temperature is a measure of atomic molecular motion. So if we're at 0 temperature, that means we have 0 motion, no motion whatsoever. That crystal, perfect crystal at 0 Kelvin, has an entropy of 0. Okay, now why would that be? Well, let's think about it. Imagine you're at room temperature and we've got atoms of iron or lead, say it's perfect. And they're vibrating at the surface. So you got these atoms that are vibrating. And as you cool it down, they vibrate slower and slower and slower. And you're getting colder and colder and colder. And you get down to 5 Kelvin. And then to 2 Kelvin, and then to 1 Kelvin. And what happens at 0 Kelvin? Complete lack of motion. Well, how many microstates would that be at 0 Kelvin? If nothing's moving, there's no vibrations, no rotations, no translational motion, diddly jack squat at 0 Kelvin, that's 1 microstate. Remember Boltzmann's equation? If the microstates equals 1, then the entropy is Boltzmann's constant times the natural log of the number of microstates. But remember, the log of 1 is 0. Boom! Thank you, Boltzmann. So by definition, a perfect crystal at 0 Kelvin has an entropy of 0 because of Boltzmann's equation. Who cares? Why does that really matter? All right, that's going to provide us a reference point. That makes entropy different from enthalpy or internal energy. All right. We are now able, because we have a reference point of 0, we are able to actually determine the absolute entropies, not changes in entropy, the absolute entropies of any substance, because we have this reference point of 0. So what we can do is just, if we want to calculate delta S, take the reference point of 0 as your initial state, and then have that substance at some other state, right? That's a non-zero state, which we could measure that delta S, right? If we can get that delta S, but that delta S is final minus initial. So final is the entropy at the state we're at, minus the initial, which would be 0, that means the change is the absolute entropy for that substance. So we actually, if you look in Appendix D or any thermodynamic tables, you'll see lists and you'll actually see absolute entropy values. Hey, pretty cool. So again, that is not possible. We are not able at this point to get enthalpy or internal energy values for a specific state, but we could get the change between two states. We can measure those. So that third law of thermodynamics is useful when we're actually going to be calculating entropy changes now, because we did entropy changes in the last video, but we did it based on the reversible heat flow divided by the Kelvin temperature. And that was extremely limited because of the reversibility constraint of that heat, pretty much only good in our everyday lives for phase transitions. So what if we're doing chemical reactions or some other process that's not going to qualify as reversible? We're going to utilize this third law of thermodynamics to be able to calculate entropy changes for processes and bypass that reversibility issue. So we won't need to use that equation. Very nice, very cool. So that's a brief, this is just a short video. I just wanted to review the first law of thermodynamics for you, introduce the second and third law, and you're going to see where these two laws come into play for some of the thermodynamic equations you're going to be using all the time. I probably won't test you on deriving these equations as much as I would like to, but at least if you dig deeper, you'll have some respect for where these equations come from. They come from these laws.